Hello, everybody. My name is Haris. I'm a research scientist in Neuroblocks. So I will be giving the rest of the presentations. They will be shorter than session one. And before I start with the second presentation today, I'd like to go through the course structure using the course website. I hope that you all have access to this. This is the main course website, just in dark mode. So if you scroll down, you will see all the course units here, along with the Getting Started page. So first things first, so in the Getting Started, I hope that you have all followed the instructions on first installing Julia, and then installing Neuroblocks, and also all the dependencies that we're going to need for the tutorials. And by dependencies, I mean Julia packages other than Neuroblocks that we will be using in our tutorials. So this is what this block of code is doing. It's going to download a file with all the dependencies, and it will essentially create a new Julia environment with all those dependencies installed along with Neuroblocks. So if you have done this, if you have followed these steps before today or before this afternoon, can I please ask you to run them again, because we made some recent changes to Neuroblocks and to our dependencies. So essentially, by that I mean if you have a folder that looks like this. Oops, sorry, this is too small. Yeah, if you have a folder that looks like this, after you run that block of code, you're going to have a manifest file and a project file. So the project file is downloaded, and the manifest file is generated from the project. And never mind if your notebooks are actually here in the same directory. They could be here, they could be in a separate folder. That's fine. But what I want you to do is, again, if you have run these steps before today, before this afternoon, just delete these two files, the manifest and the project toml, and then come back here in the terminal. Sorry, open a Julia session in that same folder and run these lines again. So that way you will download the new dependencies and the new versions of them, and you will have the most recent Neuroblocks and the most recent dependencies. And for the Jupyter notebooks, yeah, it's just to be safe. I'm not sure when you downloaded them from the Google Drive link here, but just to be safe, you can download them again. But they should be stable from now on. If not, I will let you know. And again, it doesn't matter if the notebooks are in here or they're in a separate folder within that environment. This doesn't matter. Well, the only thing that matters is you will run this command on the directory where the project toml and the manifest toml files are every time that you run a notebook, basically. So, but of course, after the presentation, we're going to have plenty of time for exercises going through notebooks, and if you have any issues with the installation, we can help you then. So going back to the home page, as I said, the sessions from now on will mostly be practical. I will be giving you maybe a 10 or 15 minute presentation, which will be a conceptual introduction to the topic of that session. And the rest of the time is working on notebooks with text and code blocks on the theme of the day or of the session. And these are the themes, basically split into units. We will start this session with introduction to Julia. And then tomorrow on the morning session, we will do the differential equations in Julia and plotting with Maki. Maki is just a plotting ecosystem in Julia. So we'll do this together on the first session tomorrow. And on the second session tomorrow, we will look into essentially Neuroblocks core, how the blocks components and the connections between them, how they are structured in Neuroblocks, and how you can create your own, both blocks and connection rules for blocks. So moving on Wednesday, the first session, we will look into essentially the core components of any computational neuroscience model, which could be neurons, neural masses, and external sources. And then we will combine these with different combinations to create circuit models. That's session 2 of Wednesday. And in fact, this is the bread and butter of Neuroblocks. So this session will include 2 separate models from the literature. One model that Lily went through, the corticostriatal model of category learning. We will see a subset of that circuit. And another model that has already been published from other group. And moving on to Thursday, we will look into decision making and reinforcement learning. That's session 1 and session 2, respectively. Decision making will go through a popular model from the literature that is trying to approximate the behavioral results that we see with perceptual decision making, and is exhibiting behavior similar to a drift diffusion model that cognitive scientists use, but this time in a circuit. And the synaptic plasticity and reinforcement learning, here we will see both synaptic plasticity in a cortical model, just letting it simulate and seeing how the connections adapt over time, and also reinforcement learning in a category learning task, where we will build, again, a subset of the big corticostriatal model that Lily presented, and we will let it learn over iterations by giving it images and giving it feedback about the category that those images belong in. And finally, for the first session of Friday, we're going to look into dynamic causal modeling, and specifically spectral DCM. And we will fit models to simulate the data. We're using that. And for the second session of Friday, which is the last session of the course, we left it open because every other session includes both exercises that are more straightforward. The exercises have to do with you changing something in the code and noticing some result. But also, each session includes challenge problems. So these are sometimes open-ended problems, but definitely more involved in every case. So after you go through the material of a day, let's pick a session, the neurons, neural mass, and sources. After you go through this material, which, by the way, this exact material on the website is the same as you will see in the notebook. So when you open this notebook here, you will see exactly the same thing in a slightly different format. So after you go through the material and any exercises within it, at the end we have the challenge problems. And these are just recommendations that we give you, like some for future directions to work on based on what you have just learned. So yeah, after you finish with the previous steps, having gone through the notebook material, you can pick any one of these and work on that for the remainder of the session. So for Friday, on the second session, we left it open as a session where you can come in and work on any of these challenge problems that you have started on previous days but have not finished. Or if you want to look at some of the material that's already there again and ask us any questions, or work on any problem that you like, even your own problems, you can come in and start modeling your own circuits. So that's the last session on Friday. So I think, yeah, this is all the housekeeping that I want to do. And as I said, yeah, I will keep it short with the presentations every session, so you'll have more time to do actual coding. So, and the first presentation is actually complementary to Helmut's presentation. Helmut talked to you about why we chose Julia for NeuroBlox. I'd like to do a more general introduction to Julia as a language, because this is going to be helpful when you work with NeuroBlox through the code interface, but also for some steps of the GUI to understand Julia better will help you even in the GUI. Right, so what is Julia? So Julia development started right here at MIT at 2009. That was the very early days, and version 1.0 got released almost 10 years later in August of 2018. And Julia has been growing basically throughout that time and from the 2018 onwards, and we'll see some numbers on that. So Julia is a dynamic interactive language. It's intuitive and it's expressive, where you can easily write high-level syntax. And essentially, by high-level syntax, I mean anything that's not close to machine code, as for instance C is. And it's built upon types and multiple dispatch. So we'll talk a lot about types and multiple dispatch. It's two very core concepts of Julia. And one way of think of this design is an alternative to the object-oriented programming design that, for instance, Python has. You will see more of this in both today in the tutorial, but also tomorrow. And yeah, Helmut also mentioned this phrase, which Julia works like Python and runs like C. It's essentially this phrase sums up all the previous points, and by that we mean that it's an expressive language. It's easy to write, but also you can make it very performant with a few extra steps if you take them. And also, just to get this out of the way on the first slide, Julia is one-based indexing. If you're coming from Python, yeah, there might be some shortcomings. I find it hard sometimes to switch between the two, but basically indexing in Julia begins from 1. And by this I mean in any collection of elements, the first element is index 1 in Julia, similar to MATLAB. Right. So I'd like to go through all these points, all these features of Julia that I mentioned one by one. And first, what I mean about Julia being dynamic and interactive is that Julia is a compiled language, but you can very easily work on it in a dynamic environment where you write lines of code, you evaluate those lines of code, and you move on to the next one, similar to Python and MATLAB. And here are 3 interfaces where you can do that. First one is the REPL. The REPL stands for read, evaluate, print, loop. It's exactly what it says on the tin. You write your code line by line. The Julia compiler reads that code and evaluates it, and it gives you a result immediately on the next line. This is easy to do, especially if you're prototyping, or if you want to check something very quickly. Maybe harder to develop, longer pieces of code just in the REPL. But then you can move on to something like VS Code. VS Code has a Julia extension, which I think works great. So there you can see an example that as the person is typing a command, you have the autofill of Julia functions that start with MA, for instance, map. And then next to that, you also see a panel that gives you the docstring of map. That is, that is fetched from Julia's documentation. So it tells you exactly what map is doing as you type. And also, it's very handy for plotting, because it's time that you plot something with your code. Then a second panel will open here, and you will see that plot there. And you can even flip between the history of plots in your current session. So it has this history component. And also, there is a REPL open on the bottom. This REPL on the bottom part is exactly the same as that REPL. So you can even type commands directly there, or you can evaluate your commands from the script that you have there. And you can evaluate them one by one, or you can run the entire script, and then you're just going to get the final result printed. And a third option, which is actually the main one that we're going to use for this course, is Jupyter Notebooks. You might be familiar with Jupyter Notebooks from Python. This is exactly the same structure. Essentially, Jupyter itself supports both Julia and Python, and R too. And in a Jupyter Notebook, it's a handy interface, especially if you have lengthy pieces of text that are longer than single-line comments. So as you can see there, we can have any text. We can have text blocks and code blocks interspersed in one notebook. And this is exactly what every page on our website looks like. And this is exactly the same in the notebooks when you open them. So I would recommend everybody using those notebooks that we have. But of course, you're not limited to them. So for instance, if you have VS Code already installed, it's one extra step to install the Julia extension in VS Code. And you can just copy-paste the code from the website to VS Code and start evaluating it there and start running it there. That's completely up to you, and we can help you if you want to set that up. But the Jupyter notebooks are there, and they're already ready. Now, the second claim that I made is that Julia is intuitive and expressive. And here I'm just showing you an example that is very much relevant to ours. This is a function that finds a spike and keeps the time for that spike as it integrates a model. And we can see the expressiveness here because as you can see on top, there is this using unitful line, where basically the unitful is a package that comes with actual physical units, right? So we can easily import this package and pick 3 units that we want to import from that package and use those units immediately in our code, almost the same as we would in paper, right? You can see that R is equal to 100 megaohms. That's standard Julia syntax that the Julia compiler can read and a human can read very easily. And even within the loop, so within the first spike function, we have this extra expressiveness because we're not limited by some rules that other languages impose. For instance, in MATLAB and Python, even in R as well, the documentation, the official documentation, will make the claim that try to use vectorized code because this is faster, right? So if you wrap everything, if you organize your data into matrices and vectors and doing operations with linear algebra, basically, that's going to be faster than looping over element by element. In Julia, that's not the case. You can use vectorized operations, or you can use loops, and the performance will be almost the same. So you have this extra expression, as you know, like it depends from person to person, of course, but I would make the claim that it's easier to read out a loop versus reading matrix multiplication and figuring out exactly what's happening. But also the fact that Julia is expressive comes from the fact that it allows you to build, to essentially design your own syntax on top of the language syntax that is already there, and that is through macros. So macros help you, make those, domain-specific languages within Julia. For instance, on the bottom left, you can see differential equations where you can type in a system of differential equations symbolically, right? That comes from modeling toolkit that Helmut mentioned as well. So Julia is able to parse those symbols, and it eventually creates this differential equation system because of these macros that you can see, the at variables and at parameters, for instance, and at equations. Those things tell the Julia compiler that now you're gonna see a block of symbolic code with maybe some symbols and some default values, or some equations split by the tilde symbol. So this extends the language capabilities a lot. And similarly, if you wanna, for instance, solve some optimization problem, you can use jump. And in jump, you can use a similar, very high-level syntax of first you start with a model, and in your model you pick your optimizer, and then you just iteratively add stuff to your model. For instance, you add a variable x, and x is strictly positive, non-negative in this case. You add a y that is bounded from both ends. You add an objective function, you add some constraint, and at the end you can print the model, and you have this nice symbolic print of your model. And if I were to show you one more line, then you can actually solve this model using the optimizer that you pick, and it gives you the, whatever minimizes your objective function. But also, of course, and this is the reason why we're here, NeuroBlox, shares this value. It's very easy in NeuroBlox, as you can see there in that small block of code, to just define the two neurons. In that case, we have an excitatory Hodgkin-Huxley neuron and an inhibitory Hodgkin-Huxley neuron. And then we create an empty graph, because every model in NeuroBlox starts as a graph. And we connect the inhibitory neuron to the excitatory one. So this simple model with two neurons connected one way can be defined in these few lines of code. Now the next thing, as I said, types and multiple dispatches, they are at Julia's core. But multiple dispatch is this is a quote from Wikipedia, and in more layman's terms, it's this property where you can have the same function, you're using the same name, having different methods implemented for it. And by methods, we mean the combinations of its arguments can be different. Some methods can have more or less arguments than others, or some methods can have exactly the same number of arguments as others, just with different types, right? So you can see the definition of an f function having two methods, right? The first method works with only floating point numbers with 64-bit precision. And then we define the second method that works with any number. Number is an abstract type, over floating floats. So as you can see, when we call f using a float 2.0 and an integer 3, then the second method gets evaluated, right? Because that's the best match that we have. But if we call f with a 2.0 and a 3.0, then the first one gets called, right? Because both of those numbers are floats, and they're floats 64 by default in Julia. And you can see proof of that at the end. That symbol between float and number, that means subtype. So this is just a logical comparator of types, if you want to. that you compare float to number, and you get true because you're claiming that float is a float is a subtype of number. So that's why those evaluations work. And now types, float 64s and numbers, those are Julia types, but also you can define your own types, and we will do that tomorrow when we define our own blocks. And on the right here, you can see an example of defining a structure called mytype. Structures are are collections of elements. They're like composite data types, and within your structure, you can explicitly, cast a type on any of the variables that the type holds, or you can just leave it blank, and you can take any type of input. For instance, here in mytype, X has no type, right? So X can be any type in Julia. Y is strictly an integer, and Z is a float 64, right? So we can see that mytype, when the first thing is a string called hello, perfectly works. And the combination of these two concepts, custom types with multiple dispatches, can extend Julia's features by basically unpredictable amounts. You can do so many things, and borrowing this term from complex systems, we can see emergent features in the language, and you will see an example of that. And by emergent features, I mean we can take types and functions that are not designed to work together, but they just work together, maybe by defining one more method, or maybe doing sometimes with adding no extra code, but sometimes with minimal extra code. So we see this unpredictable behavior coming here and there that are welcome features to have. Now on performance, this is the runs like C parts of that famous mantra. Here I'm just showing you some benchmark with popular functions. Some of them come from linear algebra, like some matrix multiplication or matrix statistics. Some of them are just recursions, like there's a recursive calculator of the Fibonacci sequence. And as you can see, on the x-axis here, we have different languages, and they're all compared to C. That's why C is collapsed in one point. And as you can see, Julia is very much approximating C behavior in most of those benchmarks. And you can see this in stark contrast with other high-level languages like MATLAB, R, Octave. Now, I also want to make a comment about the Julia community. Discourse.julialang.org is a forum dedicated to the Julia language, and it's highly active, and you can get an answer on any question that you have there. And if it's not there, it's going to be on the Julia Slack. That's the general Julia Slack that you can join for free. There's a link through the Julia webpage. But even these are some statistics from the 2023 user survey, and you can see that ever since Julia 1.0, which is the beginning of the x-axis, that's 2018. You can see how the community has been growing, both of active users and also of the page views. And also, in terms of learning components, if you want to explore Julia more, this also comes from the developer survey 2023, where the survey was asking participants what resources that have you found most useful when learning Julia for the first time, or when learning to do something new in Julia. So most people answered that they use the Julia manual, and I add this slide here because I know that sometimes the official manual can put people off. And then it's not always well designed in every language or in any software. But in Julia, this is very much the case. I think the Julia manual itself is very useful. So I would urge you, if you want to look more into Julia, to definitely look into the manual, but also on the other main categories. For instance, Julia Con presentations and YouTube tutorials and Julia books. We have references that fall into these categories in the introduction to Julia page, and you will see that on the website. So yeah, if you want to learn more about Julia, you'll have plenty of resources, and also feel free to ask us both today and any other day during the workshop. And yeah, I think this is my last slide for now. So do you have any questions on the introduction to Julia? No? Okay, cool. So we can start with the actual exercises, so you can navigate to the Introduction to Julia page. You can do this both from the side menu, by the way, but also from the home page when you have all the units. And the first notebook is the Julia intro, where basically when you start running Jupyter for the first time, you will get a window like this, right? So you need to navigate to the folder where all the notebooks are and open Julia intro. And you will do the same with any future notebook. Just one comment on the Julia intro. This first notebook is that this is quite lengthy, but it has a lot of useful material. But I would say, in the interest of time, I would urge you to skip the performance session, which is I thought I had it open. Yeah, from here towards the end, you will see after the type stability. Definitely go through that. Yeah, actually, sorry, it's not. Sorry, that's my bad. So yeah, after this, the section on functions that is here on cells, around 100, 180, you can stop and switch to the second notebook, and because this last bit of the notebook is about performance and how Julia managed to be so performant and what you can do in your Julia code to make it run faster. So I left it in, but in the interest of time, we can skip it for now and move on to the second notebook. And you can always come back if you're interested in performance or how Julia does it. You can come back and do this last section. Yeah. So yeah, feel free to start with the notebooks and ask any questions either on Slack or raise your hand, and we'll be around to answer them.